Imagine you are trying to guess someone's weight just by looking at their height. To train our model from scratch, we need a simple baseline piece of data to learn from. Here, we define a single input feature called x, which represents our input data point, and a target label called y, which is the correct answer we want to predict. We also initialize our model's weight to 0 because it has not learned anything yet. A common mistake beginners make is initializing weights to massive random numbers, which can completely destabilize the early learning process. Before a model can improve, it needs to make an initial guess based on what it currently knows. We calculate this guess by multiplying our input feature by the current weight, which gives us our predicted value. In machine learning, this step is formally called the forward pass. Right now, our model predicts 0 because our weight is 0, which is far from the true target. A frequent mistake here is forgetting to pass the input through the weight, leading to completely static predictions. To measure exactly how wrong our model's guess is, we need to calculate the raw error. We find this by subtracting the true label from our predicted value, showing us the gap. This raw distance tells us both the direction and the magnitude of our current mistake. In this case, our error is -6, meaning our prediction is much too low. A common error is subtracting the values in the wrong order, which flips the sign and confuses the update logic later. To turn our raw error into a formal penalty, we calculate the squared loss by multiplying the error by itself. Squaring the error ensures that the loss is always a positive number and heavily penalizes larger mistakes. Think of loss as a score, where a lower number means a better, more accurate model. Right now, our squared loss is 36, which gives us a baseline for how poorly we are doing. A major pitfall is using the double asterisk operator in pure Python loops, which can slow down performance compared to direct multiplication. Imagine you are standing on top of a foggy mountain and want to find the lowest valley floor. Since you cannot see the bottom through the dense fog, you must feel the slope of the ground beneath your boots. If the ground slopes downward to your left, you naturally take a careful step in that direction. This intuitive process of feeling the slope to find the lowest point is exactly how gradient descent operates. A common misconception is thinking the model can see the global minimum instantly without exploring the slope step by step. The mathematical term for the slope of our loss mountain is the gradient, which tells us how the loss changes when we adjust the weight. To find this slope, we calculate the derivative of our squared loss function with respect to our weight parameter. By applying the chain rule from calculus, the gradient simplifies to 2 times the input feature times the raw error. This resulting number points us in the direction that increases the loss fastest, so we must move opposite to it. A classic mistake is omitting the input multiplier, which makes the gradient completely blind to the actual data. If we updated our weight by the entire gradient value, our model would take a massive leap and overshoot the valley completely. To prevent this chaotic behavior, we introduce a small scaling factor called the learning rate, often denoted as alpha. Think of the learning rate as your stride length when hiking down that foggy mountain slope. We will choose a cautious stride length of 0.05 to keep our steps steady and controlled. Setting the learning rate too high is a dangerous mistake that causes the loss to explode into infinity. Now we are ready to perform our very first optimization step by updating our weight parameter. We adjust the weight by subtracting the product of the learning rate and the calculated gradient. We subtract because we want to move downhill, opposite to the direction of the steepest descent. Our weight successfully moves from 0 up to 2.4, which brings it much closer to the ideal target. A frequent bug is accidentally adding the gradient instead of subtracting it, which drives the model uphill away from the solution.
Let us perform a second forward pass to verify if our single optimization step actually helped the model improve. We calculate our new prediction using the updated weight value of 2.4, yielding a prediction of 4.8. When we compute our new squared loss, we see it has plummeted from 36 down to just 1.44. This dramatic drop proves that our gradient descent formula successfully guided the model closer to the truth. A common error is forgetting to recalculate the prediction after updating the weight, causing the loss to appear unchanged. In machine learning, passing through our entire dataset one single time is formally called an epoch. To automate this process, we can wrap our forward pass, gradient calculation, and weight update steps inside a clean loop structure. We will run this training loop for 4 distinct steps to observe how the weight steadily adjusts over time. Watch how the weight climbs higher during every iteration, while the corresponding loss value continuously shrinks. A frequent mistake here is hard-coding the gradient value inside the loop instead of recalculating it dynamically each time. As our loop continues to run, you'll notice that the changes to the weight become smaller and smaller with each step. This stabilization happens because our error is shrinking, which naturally reduces the size of the calculated gradient. This beautiful self-correcting phenomenon is known as convergence, meaning the model is settling peacefully into the bottom of the valley. By the 10th epoch, the loss has dropped to an incredibly tiny fraction close to absolute zero. A common mistake is stopping the training loop too early before the loss curve has fully flattened out. We have successfully built a complete gradient descent optimization loop from scratch using absolute first principles. Let us inspect our final weight value to see how close our model got to discovering the perfect mathematical solution. The final weight evaluates to exactly 3.0, meaning our model can now predict the target flawlessly. If we multiply our input of 2 by this final weight, we get our original target of 6. You now understand the core engine that powers the training of every massive artificial intelligence model in existence.